All right. Hi, everyone. Um, so today we're going to be talking about greedy algorithms. So that's our discussion today. So talked a little bit about greedy algorithms last week when we were discussing Dijkstra and what exactly it is. So talk about how it's greedy, why it's greedy. But today we're going to get into like greedy algorithms and what they are and some examples. So our objective is like to understand why we would use greedy, and in general, that's for optimization problems where we want to like optimize something. We want to choose the best, or yeah, something optimization usually means we're trying to find like the best solution, or yeah, you're trying to find the best of something, or you're trying to optimize something, make something some part of something that's an attribute, but yeah, part. So yeah, and we're talking about greedy strategies, so how we can possibly approach things with a greedy approach. When do we use greedy algorithms? We're going to discuss that because sometimes they don't work, but we're going to discuss that. And we're going to talk about, okay, this is no longer project 2, but these old slides, I guess, but we're going to talk about Huffman's algorithm, and we're going to talk about graph coloring. So those are our two main examples for today. So, okay, so optimization problems. So yeah, in general, optimization problems, you want to find the best solution. And as an example, image classification algorithms want to minimize the percentage of images that classify incorrectly. So if you have like, maybe it's a machine learning model, I don't know, and it classifies images, maybe you want to optimize based on the percentage of images classified incorrectly. So you want to like make sure that you're choosing or doing the best you can, like choosing the correct image the most amount of time. So you're optimizing for that. And algorithms that solve optimization problems usually go through a series of steps to produce that. And so maybe you would ask, how should an algorithm make decisions to produce an optimal solution? Well, with greedy algorithms, the general idea is that you're choosing a local maximum or local best in order to reach the goal. So if you think about just generally, like if you have a problem, maybe there are a bunch of parts to it. If you try and choose the best solution in each part, that's what the greedy approach does, is it tries for every little part of the problem or little part of your solution, it's going to try and choose the best for that little part. And hopefully over the whole thing, it'll choose the best. Now it sounds confusing at first, but we'll get into like more details about that. So yeah, for greedy algorithms, that answers the question of how can we make decisions to produce an optimal solution. And so you make the choice that looks best at every step, which is kind of mentioning, and you hope that, yeah, the best looking choice each time will result in the optimal solution. We'll talk about later that that's not always the case, but there are many examples when it is. So maybe examples in real life, or you're currently standing at the top of a hill. Yeah, and that like might be in real life, right? You want to end up at the ground level. So the greedy strategy is to walk 1 foot in whatever direction is the steepest downhill. So maybe it's possible that there are problems that this wouldn't give you the best solution. Maybe it would take more steps because like this may not give you the optimal solution, because even just thinking generally, right? If you have a steep hill, maybe there's one step that's super steep. So you start going this direction, but really more of the steps are steep this way. So it would actually be faster to go to the right. But the first step is like steep going left. So maybe you go the wrong way. But that's why greedy can sometimes be wrong. But in general, it's a really good approach, right? Because if you think about it, just choosing the steepest step each time will probably get you a pretty good solution. It'll get you down quickly. So it's just kind of generally a way to think about greedy, maybe seeing why sometimes it's not the best, but in general, it's a good approach. Okay, but now on to like more concrete discussion. Okay, well, first we're gonna have a question. So you have a pile of tomatoes, each with a variable weight. You also have several bins, each with a maximum weight capacity. Pick all the greedy strategies. Okay. And I'll give you a minute to answer. And you can pause and try and answer it. All right, so let's see, is the first one greedy? Not really, right? Because just throwing into a random bin, that's not a greedy approach. Like you're not choosing an optimal, like with greedy, you're trying to choose the optimal solution at each step. And there's no optimal solution here. Like you're just randomly doing it. So that's not greedy. Wait until you have all the tomatoes, then think through all possible combinations. It's like the optimal combination. But that's not greedy either, because that's brute force. You're going through every combination. And greedy does not go through every combination. It just kind of chooses. And so it's good in terms of time complexity for that reason. when you actually have greedy algorithms. But yeah, this is not greedy because it's brute force. How about C? For each tomato, scan the partially filled bins and place the tomato in the partially filled bin with the most open space. None of the partially filled bins have enough room for the tomato, and then open another bin. That absolutely is greedy. It is actually known as the bin packing problem. And you can prove this is a two-factor approximation. There are better approximations. And yeah, problems like this. They're good problems. They're very interesting anyway. Yeah, and so, but in this case, right, the reason why this is greedy is because you're at each step, right, you're choosing the bin, which it would, you're choosing the bin which it will like fill the most space in, right? Like you're trying to make sure you're minimizing, in this case, you're like minimizing unused space because for the open space, you want to like try and fill whatever, like if there's a lot of space left, you want to try and fill it. So what you're basically doing is minimizing unused space. And that's kind of the strategy you use at every step. And so it won't get you to, this actually won't get you an optimal, but it's the greedy approach. So that's why this is greedy, because at each step you try and optimize and hope that it gets you the optimal solution in the end. Yeah, and as we can see, right, it involves making a reasonable optimal choice at each step. So it's and yeah, random choices are not optimal, and exhaustive searches are not greedy. Okay, so when are greedy algorithms effective? So they're usually effective when a series of locally optimal choices always leads to the globally optimal choice. And there are examples of that. For example, Dijkstra's last week we talked about. If you choose the, after you relax the edges, if you're choosing the vertex that's the shortest distance of the unvisited vertices, right? Shortest distance away from any of the visited ones, right? At each step, that will get you the shortest single source shortest path to all the vertices from your source. So just greedily choosing at each step will get you the optimal choice. And Huffman trees, which we'll see in a minute, will also, using greedy also works for those. But yeah, some are just approximate. For example, the traveling salesman problem, TSP, which is a pretty important problem, or a pretty prominent problem, I guess, which is you find the shortest tour, their positive weighted graph. So that's a tour is when you start at some vertex and then take some edges and visit every other vertex exactly once, and then you end up right back where you started. Yeah, so that's what a tour is. So you try and find the shortest tour, their positive weighted graph, and the exact solution is that it takes exponential time. It's an NP-hard problem, and so NP-hard problems in general, or NP-hard problems require exponential time to solve, and that's an example of one. There's a greedy approach which will not get you the optimal solution, but it'll get you within 1.5 times the optimal solution, and it takes n squared long in time. So if you want the actual solution, then greedy is not going to work, but it can get you a good solution. So in real life cases, that might be the reasonable thing to do. Okay. Yeah, so also just looking at this picture, right? Maybe greedy will find the local optimum, but not the global optimum. Okay, moving on. Huffman trees. So this follows from the optimization problem to compress a file into minimum number of bits. So that's the idea of Huffman trees. It's a full binary tree where every leaf corresponds to a character from the file. Basically what you do is you collect frequency. So you have like a frequency table of the different characters. So how many times they show up in the file. And then you build a tree whose path represents the characters. And characters with larger frequencies have shorter distances from their root. And then branching left to right from a given node is 0 or 1. So like left might be, or left is 0, right is 1. And the path that you take to arrive at a character's leaf node is the Huffman encoding. And so yeah, it's good for like data compression. And you think about it, this might make sense if you want to try and minimize the number of branchings it's going to take to get to certain characters, right? Like in a tree, if there's something that shows up, like if we want to try and get as quickly as possible, like it would make sense, right? We want to get as quickly as possible to things that show up more often. So if there's a vertex that, or not a vertex, but if there's like a character that shows up a lot, they want it higher up in the tree because you don't have to traverse as far. And Huffman encoding allows for us to have like the best balance of that. So it doesn't take too long to reach characters that we see more often. That's the entire idea, is trying to optimize just for that. Okay, so here's an example. If we have, this is an example of a Huffman tree, right, as our sentence, maybe that's what's in our file. Well, this 36 here is the number of characters, and we'll see how we actually build it in a minute. Maybe you kind of can see what's going on here. The space character shows up 7 times, so we're going to see it over here, and the A shows up 4 times, so it's here. And yeah, so the main idea is like with Huffman tree, you're trying to minimize the heights that you're gonna have to go through to actually get each character from the tree. Because if you have to get this space 7 times, then you want it higher up in the tree, right? Because then you'll have to traverse as far, like we mentioned. Meanwhile, like L shows up once, so it's okay to go further down the tree because in total, you're not gonna have to go as far as many times. But okay, that's the idea. Yeah, and so we'll see how we build the tree. But on the next slide, but Huffman trees use greedy. Huffman codes are greedy because the least frequent codes are have the longest path in the tree. So that's why they're greedy. We'll see what the greedy approach is that allows us to have this property. The greedy choice property is if X and Y have the 2 longest counts, so we have X and Y each have a count, and then the lowest counts of any of the counts. It'll help visually in a second. Then the optimal algorithm is just going to have them at the same time. And it solves the problem of finding the optimal encoding. And and the code depends on the text given because, of course, like those are the characters, right? And the whole idea is we want shorter codes, shorter paths, or fewer parents for characters with high counts, but we are okay with having a longer path through the tree for things with lower counts. So, okay, this is pseudocode. Before we go to the pseudocode, let's just use the example because I think that helps a lot. Okay, I like this example, so we're going to the example, then we'll go back to the code because I think that's going to help us understand what's going on here. So let's just say we have a file, and I don't know, A shows up 45 times, B 13, C 12, D 16, E 9, F 5. So we're going to start. Don't worry about the Huffman, the thing below it yet. But we're going to start with this, right? Where we actually just separate them. We say, okay, these are going to be our leaves, right? Because the leaves are where all of the values are, like all the characters are. So these are going to be our leaves. Now we need to actually construct our tree, right? Because leaves on their own, right? This is not a tree, it's just like disjoint nodes. So how are we going to do that? Well, at each step, what we're going to do is we're going to choose the 2 smallest counts, and we're going to put them together. So we put together E and F because they're the smallest. And so we have 5 and 9 come together and make 14. And we put the larger one at 1 and the smaller one at 0, just for simplicity. But it should be the same height either way. But now we no longer have E and F because we've joined them. And so now we have the value 14 instead of the values in the 5 and 9. But 14 is not the smallest or second smallest, 12 and 13 are. So we join those 2 trees together, first C and B. And now we're left with these 3. We're left with these 4. Now the 2 smallest are 14 and 16. So we join those and we make 30. And maybe you can even see kind of like which data structure we might use. And we'll talk more about that in a minute too, when we actually talk about the code. But yeah, we have 14 and 16, right? And we join them to make 30. And we put 30 back as we have to choose from still. And then 25 and 30. We join those. And then we join, now we have 45 and 55 and we join those, right? And this is our entire tree. There were 100 characters. And what we optimize in this problem is basically the sum of the path lengths. So like if we have to go 45 one, like we have to 45 times we have to go down one. And then 16 times we have to go down and make 3 choices, plus like 16 times 3, right? This is the total number of times we're actually gonna have to make a check if we actually want to find a character in the tree, for example. Or like if we actually want to make the whole file from the tree. And then this is how we would do it, right? Like there would be 3 checks, 1, 2, and 3 to get to C as well. So it would be 12 times 3. And so this sum, like in order to make a tree that minimizes this sum, that's what the Huffman encoding problem solves. It basically tries to minimize the total number of times we're gonna have to go through the tree if we want every character, or the total number of like height checks or number of checks we're going to make. So that's the idea of what it's solving, and this is the approach we take. Because at each step, we're basically taking just the smallest 2 and putting them together. And maybe that makes sense kind of intuitively, because just thinking intuitively for a second, right? Let's say we're at the second example. Oops. We're at the second example here, or yeah, second step here. Or let's do somewhere we already have things put together. So we have the third example. We have 14 and 16. Well, even though E and F are separate, right, there are 14 total characters there, right? And there are 16 total characters with D. So we're okay with having those as low down as possible in the tree, because we want to minimize the number of checks. So if we want to minimize the number of checks we have to make to go down the tree, then grouping them together makes sense, because that means that these are going to be as low in the tree as possible. So we're going to have to make this, we're going to have to make more checks to get to these, but that's okay because they are the least frequency, which means things that are greater frequency like A and this tree here, right, will be higher in the tree. So it's going to take fewer steps to get down to them. That's exactly what we want to solve. So maybe it kind of intuitively makes sense why this works. But okay, this is how the algorithm works. But as I mentioned a minute ago, maybe you can kind of see what kind of data structures we might have to use. So you can kind of pause and maybe think about it for a minute. But I'll go ahead and like start talking about how we would actually write the code for this. Because maybe what you notice is that, let's just start at step C, just as an example. At step C, remember, we choose this 2 smallest. And when we choose the 2 smallest, we're going to remove them, join them, and then put it back as this thing. So, and notice it still has some sort of attribute to it, right? So what kind of thing might this make sense to do? Like we can remove the smallest and then put something in, and then we can remove the smallest again. Maybe you're thinking heap, and that would be exactly right, or priority queue. So yeah, we can use a priority queue for this. And in the code, you can see here, that's exactly what we do. We use priority queue. And that's why, right? So C is a set of characters. We have n equals C dot size. We have our priority queue. And from I equals 1 all the way up to n, so the number of characters, we're saying that x is equal to node ci. So basically, we're just figuring out the frequencies. So the first thing we do is figure out the frequencies, basically make our frequency table. And then now we're actually going to use our queue, right? So this is basically the beginning part is just making our frequency table. Then we use our queue. We filled our queue first, or originally we just put all of the frequencies into our queue. So in this example, we put A45, B13, C12, D9, C16, E9, and F5 into our queue. And then remember, each time we actually go through, we should remove 1 from the size of the queue, because we're taking 2 things out, but putting 1 thing back in. So every time the queue should go down by 1 in size. So while it's greater than 1, once it's 1, we've built the whole tree. We make a new node. We make the left node the smallest, and the right node the second smallest. So we pop twice, and then we add their frequencies. That's the frequency of the entire tree, right? Which makes sense, right? That like here, it was 5 and 9, 14. We add their frequencies. That's the frequency of this new node, and then we put this new node back in our queue, and we keep going. So that's how this code works, and maybe it kind of makes sense now. Hopefully it does. If you have any questions, of course, you can message me. But that's the idea of trees. So we have a poll question here. Maybe we haven't gone over this particular kind of question yet, but hopefully you can kind of see how to solve this. And if not, let's go over. But yeah, what's the proper encoding of face and decoding of that, of this monstrosity here? Okay, you can try to pause. All right, starting over. So encoding a face. So how would we do this? Well, okay, let's see. First, we need to get F. So how do we get F? Well, F is 1, 1, 0, and 0. So it's 1, 1, 0, 0. We find A is just 0. C is 1, 0, 0. And E is 1, 1, 0, 1. And the way we did that, notice one for E, I'll just do E. The other ones, hopefully you kind of see from this example. To get to E, it's 1, 1, 0, and 1. That's what we had last. And yeah, to get to A, it was just 0. That's why we have is just a 0 for A. Okay. So that should be face. Now, the next question, or next part of the question, is decoding of 0, 1, 0, 1, 1, 1, 0, 1. So let's try. So, well, okay, 0. That's just A. Anything that starts with a 0 is just going to give us A, because A is the only string that starts with 0. So that's A. And then we have 1, 0, 1. That gives us B. And then we have the next one. After 1, 0, 1 is 1, 1, 0, 1. That's going to give us E. So what we have here is, it looks like this one is the last answer. And there we go. So that's how we would do a problem like this. And so it should we should have answer, I guess they're all answer A, so no matter which one you answer, you're right. But no, it's the last of the answers. Yeah. Cool. Okay. So that's how we do that problem. Hopefully that makes some sense. And we'll move on to poll question number 3. The following statements explain how they are greedy. So we can try and answer that. You can pause if you want. I'm going to go over the answer now. Okay. So the answer, let's see. Hoffman trees can only contain characters. That doesn't make it greedy. That's just a problem constraint. Or a tree constraint. Yeah, it's just a constraint, right? Most frequently used characters get the shortest encoding. That absolutely makes it greedy, right? That's the entire idea, is that at each step, right, we choose the least frequent ones, and that ends up meaning that the shortest encodings, or the most frequent encodings, right, are not chosen until the end, so they get the shortest encoding of all. So this absolutely is why they are greedy. They use a max heap to solve the problem. That doesn't make it greedy. You can solve plenty of problems with max heaps without greedy solutions, so that's not true. The Hoffman algorithm is recursive. I mean, yeah, it doesn't have, just because you use recursion does not make something greedy. So it's not that one. So the answer is 2, and only 2. Okay, cool. So now we're talking about a different problem. So this problem is kind of interesting, actually, because there are different ways of putting this problem. But I think there are different ways of thinking about the same problem. Like, there are other definitions of it, but we're just going to learn about, and we're just going to think about it as the graph coloring problem. And the whole idea of the graph coloring problem is, how can we assign a color to every node of a graph such that no two nodes that share an edge also share the same color? And how do we do this with as few colors as possible? So one thing you could always think of is, oh, just give every node in the graph a different color new jump. And okay, that would solve the first part, right? That's a way of assigning them, but that doesn't give us any information about the second part. How do we choose as few colors as possible? So it's tricky, right? Yeah, it's a very hard problem. So let's go into it. And I mean, when I say hard, I don't mean like it's hard to solve. I mean like it's an actual like NP hard problem, as in like it, okay, as in like it's. We'll get into more details later. But yes, it's a hard problem. Okay. Problem information. So the function you're going to make will take a reference to the form graph. So if we actually write a solution, you have your class graph, right? You have a public, and then you have instructor and all that. Okay, and maybe you rank your colors, 0 to 5, red to purple. The first node, you're going to assign red, next blue, and so on. Okay. And okay, that's kind of the problem information. Is we want to return the colors, and maybe you're given an adjacency list within your graph, right? And that's what the graph is. Okay. So maybe you're thinking about, how do I use greedy? So your method signature will look something like this. Let's say you're given this method signature. You're given a vector of string, color, and you're given a graph, right? Graph, a reference to graph. The method takes in a reference to the graph object, like we said, and the method will return vector strings. And in uppercase, and they're the colors of the nodes, the way you color them. So maybe you color them red, then blue, then green. Maybe those are the only ones you need. And then maybe it's like there are 4 nodes. Maybe you label them like red, blue, green, blue, or something. So that's what you would return. It's just a vector of strings with that. And the constraints are, it's undirected graph. It'll always be a connected graph. We won't give you an unconnected graph or disconnected graph. And the number of vertices is less than or equal to the floor of the square root of the maximum value of integer in C++. And the number of edges is less than or equal to b times b minus 1 over 2. So it's just saying it can be any kind of graph, but it just won't have, we won't have multiple edges between each vertex, but it can be it can be like a K graph. I forget what it's called, but like that's where all edges are connected to one, all vertices are connected to one another. Yeah, I think it's something like that. Okay. Anyway, maybe that's just like problem information. Maybe you can kind of think about, how would we approach this greedily, and how would we just approach this problem in general? So first, let's just talk about how we generally solve. So let's tackle the problem coding interview style. So if I give you this problem, right, and I'm like, okay, color the edge or color the vertices. So basically choose a color for each vertex such that none of its neighbors have the same color, right? So if I choose blue, none of its neighbors can be blue. And if I choose yellow here, none of its neighbors can be yellow. So maybe that's a better way to say it. But okay, how are we going to choose them? What's the best way to choose them? And so on. So we're going to tackle the problem. So first, let's just start with brute force, a brief explanation, and then we're going to try and make it faster with the greedy approach. We're going to work through an example, state some pseudocode, explain, discuss runtime, and yeah, that's the idea. So let's start. Let's start with brute force. So we can go through all combinations. Okay, colors for the graph, where k is 1 through v minus 1. We can check each combination until the first one is solid. So basically, what we can try, what this is saying is we can try every single combination of colors on each of the vertices, and once we get something that works, right? Once we get the lowest number that works, right? We can try with 1. Oh, that didn't work. 2. Oh, it didn't work. 3. Oh, maybe 3 works. And once 3 works, right? We try by coloring them all. Once it works, we're done. And the problem is the runtime for this is going to increase exponentially. It's n times 2 to the n. And as the graph size increases, after a certain point, getting the most optimal solution is really slow, because like anything that's exponential is slow. So that's why it suggests that greedy strategy will be best. So we can sacrifice having an optimal solution for one that's good enough. And that's what I meant about this problem being NP hard. Is like if you want to get the actual solution, it's going to take exponential time. But if you don't care, it doesn't have to be necessarily optimal, but it has to be close to optimal. We can use a greedy approach. We can use any sort of approximation algorithm. But in this case, we're just talking about greedy approaches. So you can use a greedy approach and it can run a lot faster, even if it doesn't necessarily give the optimal solution. And so now we're going to talk about greedy approaches for this problem. So for the greedy approach, we start at the first vertex, and one by one, we assign a color, a checking. So maybe this is a little confusing at first, but let me just draw out. Let me draw it in black actually at first, and then we'll color in the nodes. Oh wait, let's make it white actually, because it's a black background, so you won't be able to see it otherwise. Okay, so maybe it's not like this. Okay, so we start at the first vertex. Let's say this is our start vertex. And we assign one by one a color. We're checking for the first color in the list not assigned to a neighboring vertex. So let's color the first one red. I'm just kind of trying to explain what's going on with this. So now maybe yellow is the next color, right? I guess blue is the next color. So let's do blue next. Okay, so now we visit the red one's neighbors. So we start at the first vertex and assign a color by checking for the first color in his neighbors list. So now this guy here, right, is connected to red. So we can't choose red, we choose blue. And maybe we're also at this one. So we check this guy. Like, oh, well, our neighbor is red, so we can't be red, so we choose blue. Okay, now next color is yellow. Oh, we don't necessarily need yellow. We look at this vertex now on this one, and we say, okay, which color have we not chosen in our neighboring vertex yet? Or among neighboring vertices? Well, we haven't chosen red for any of our neighbors, so you can choose red here. And then now we choose the last, we look at the last one, and we're like, oh, okay, which one have our neighbors not chosen yet? Oh, well, that's blue, right? I mean, we start with, well, yeah, the way we decide is we actually look through our list, right? Basically of red and blue and yellow, whatever, and so on, no, whatever, but so on, right? And we say, okay, red is taken by a neighbor. So now I have to see if blue is taking my neighbor. Oh, blue is taking my neighbor. I can't choose red. I can't choose blue. Okay, I choose yellow. But let's look at this last one as an example. Last one, red was taking my neighbor, blue was not taking my neighbor. So we take blue. So that's greedy. And it's greedy because at every step, we're taking the earliest possible color in our color list. So whatever color is highest up in our color list, we just take that one if it's available. Like if none of our neighbors have that one yet. And we keep doing that. And that's the greedy approach. And this actually solves the problem a lot quicker. It doesn't necessarily give the optimal solution, but it solves it a lot quicker. Maybe you can kind of think about, okay, maybe this makes sense. This is reasonable to do. Because notice, like even with red, blue, and yellow, we didn't ever have to touch the yellow color because we only had to use red and blue because we never got down to yellow because we were just choosing the earliest possible one each time. You know, if we were just choosing kind of randomly, we'd probably choose Y as well, but we didn't need it. So that's why this is good. A good approach to use. Okay, so that's the idea. So we'll also look at this example. So, okay, graphs will input it as a vector of edges. So, yeah, there's 0, 1, so 0 to 1, and 0 to 4. We'll label them 0 to 1, 0 to 4, 0 to 5, 4 to 5, 1 to 4, 1 to 3, 2 to 3, and 2 to 4. Okay. In this one, notice what we do is we choose red for vertex 0. So red. Because red is, let's say our color list is red, blue, green instead. Red, blue, green. So we choose red first. And now we look at let's say we look at vertex 1 next. Like, oh, darn, we can't choose red because it's already taken by one of my neighbors. So I choose blue. And then we look at vertex 2. And vertex 2, we're like, oh, yay, red is not taken by any of my neighbors. I'm going to take red. And then we look at vertex 3. And we're like, oh, darn, red and blue are both taken because blue is taken by 1 and red is taken by 2. So I have to choose something that's not red or blue. So I'm going to choose green. And then vertex 4 is like, oh, darn, red is taken, but yay, blue is not taken. So I probably drew this wrong. Did I? No, I think it's fine. Wait, 0, 1, 0, 4, 0, 5, 4, 5, 1, 4. Oh, yeah, I forgot 1, 4. Sorry about that. So 4 could not get blue because I forgot an edge. I forgot this edge. Oops. So 4 could not get blue or red. So 4 had to get green. He's like, oh darn. But then 5 was like, yay. I can't choose red, but yeah, I can take blue. So he takes blue. And so, yeah, we just greedily go through. We choose the earliest one possible that isn't taken by a neighbor yet. That's the idea. So hopefully you can see it now after going through 2 examples. Okay. So, yeah, and we know that this is going to give us a result in which they don't share the same color because at each step, we always make sure we choose the first one that none of our neighbors have yet, which means, of course, like if we are choosing color that none of our neighbors have, then we can't share color with any of our neighbors. And that's true for every node, right? So of course, because of that, if we're always choosing one that isn't the color of any of our neighbors, then we're going to result in a graph that has no vertices that have the same color as the neighbor. So yeah, that's how we're so sure of this. Okay. And so now we're going to actually assign ranks, right? We assign 0 to red. We try and choose red first, try and choose blue, then green, then yellow, then orange, and purple. So we're like, it's a list, but it's like ordered, right? So let's go through maybe the example a little more clearly, right? Maybe like a better animation anyway, but a little bit quicker because we've gone through a couple of examples already. So current node 0, we choose red because it hasn't been chosen by neighbor. And then we go to 1. Like, well, 1, we choose the earliest possible thing we can. 2 has no marked neighbors, so we color it red. 3 has a red and a blue neighbor, so we have to color it the next to it 1 green. 4 has a red and a blue neighbor, so we can choose green as well. And 5, we're going to choose blue because red is taken, but blue is not. And so that's how this whole problem works. So yeah, we colored all the nodes accordingly. So this is what we'd output. Okay, so let's do a poll question. So what's true about these graphs? You can try and answer, you can pause if you want. Okay, so let's go over it. So let's look at the first choice. They have valid graph colorings. Oh, whoops, I guess I was in the way. So maybe I can see a little better if you just couldn't see before. Okay, they have valid graph coloring. Well, let's see. Does A have or A does have a valid graph coloring, but B does not, because these two share an edge, but also share color. So this is not true. Neither graph, well, that's not true either, because A most certainly does have a valid graph coloring. Graph A does not have a valid graph coloring, while B does. That's not true. And the last one is true. A has a valid graph coloring, and B doesn't, because B has 2 nodes which share color and an edge. So C. There you go. Okay, moving on. So now we're going to talk about our greedy approach, right? A little more. We talked about how we went over a bunch of examples. Let's see kind of like, okay, how would we actually turn this into code? So let's look at pseudo. So we can color the starting vertex the first color, and then for all remaining vertices, we color it with a color that has not been used before, right? Like if we chose red already for a neighbor, then for this one we can't choose red. But we color it with a color that hasn't been used before by any of its adjacent vertices. But we want to choose the one that's earliest possible. So if there are no more available colors among adjacent vertices, we have to pick a new color and then assign it to that vertex. So if it's something like this, right, where even if we just have two, we just say, okay, I only want to use color red. And you're like, oh shoot, I can't use that now. So you have to make a new color blue and you assign this one blue. So that's the idea, is that we start with just one color and then every time we have to use a new color, we make a new color. And we're gonna try and minimize the number of colors used. So okay, that's kind of the pseudocode or an idea of it, right? So let's start turning into code. So we start this problem, 3 basic steps. So we initialize, we color the graph, and we return the vertex colors as a vector. So we initialize, we make variables. Color the graph, so we loop through our vertices, and then for every vertex, we assign the next available color, update the containers, and keep track of them. And then at the end, we create a vector and assign them. So let's look at it. So first, let's do initialization. We hold the array to hold the color strings. The first vector is the index. We'll have the associated color, index for each color. And you initialize it to -1, but you haven't assigned any yet, right? So yeah, that's true because yeah, you haven't assigned to any at all. The second vector is going to keep track of the neighbor's vertices. So we have exactly this. C is our number of colors. N is our number of vertices, and we make a map. And we map, well, we have, yeah, a string map, and then for, yeah, it's C, like it's of size C, and it's just gonna be all the colors that we have our vector C index. So it holds the color index for every vertex. So basically what color each vertex is. We assign -1, as we mentioned, and size is 6, because each one is 6. For which colors you've taken so far. Because if we haven't taken the last one, then that's good, right? Like if we haven't taken the first one, we're going to always use it, as I mentioned. Okay. So now we're going to tackle coloring the graph. So this is how we initialize, just initializing our variables. So now we're going to tackle the graph coloring. Over vertex, we're going to mark which colors we've taken, have been taken by the neighbors, right? Because if red and blue have been taken by the neighbors, we can't choose those, we have to choose green. And we're going to use our taken container for that, so our vector. And then we find first available color. So we're going to go through, oh, red's taken, blue's taken, oh, we choose green. And then assign the color vertex. And then we reset the color vector, or the neighbor vector. And yeah, so that's the whole idea. Hopefully that's clear. So let's see. So basically, we're going to now, we're going to color each vertex in order. So we start with vertex 0, we go to vertex 1, vertex 2, so on. Because there's no harm in doing that. It doesn't really matter what order we go in. It does matter. Okay, it totally does matter. It will affect our output, but beforehand, we don't know which order is going to give us the best solution. So we just can arbitrarily go through because it, for all intents and purposes, doesn't matter. So we go through the vertices from 0 to. So we loop through the list, and for every vertex, we're going to collect the colors of each neighbor. So we can keep track of colors to avoid, because we don't want to be red, ours to color red, right, if we've already colored a neighbor. And this information is going to assign the next value. So we have our color graph, so we're going to loop through and mark every vertex as neighbor, colors as taken. So we're going to say, okay, I've taken, maybe I've taken red already, so I can't use red. And you're just going to mark all of them. And then you're going to go through all the neighbors, right? And if it's not -1, so if it is taken, if they are using that color, we say, okay, we can't choose that color. We're going to mark that color as taken for this node. And after doing that, now we have what's been taken by all of our neighbors. So now we're going to go through the list of colors that we want to use and say, okay, if none of the first one isn't taken, we're going to take, right? Because it's the highest priority one. Like if red is not taken by any neighbors, we're going to take red. And if blue isn't taken by any neighbors, we're going to take blue. But if all of them are taken, make a new color and use that. And now we loop through the loop range colors. So we get that, and since we've colored our current vertex, we break from the loop. Because now, once we find something, or it's going to break because we color it. That's the idea. And after we select a color, we need to reset the neighbor color. So yeah, like the neighbor's color has to be well, we have our neighbor color container, right? Which is tracking like what the neighbors are, but because we have a new next node, right? Like the next node is a different node, we're gonna have to reset. So that's the idea. Okay, so now we're done with the first two steps. Now we're gonna have a return vector. So last step, we're gonna collect the colors for each vertex. So we're gonna see, okay, what color did I color each vertex? And then we're gonna return. So to this end, right, solve this, we're gonna create our vector and just add the colors in string form. That's it. So we make our vector and then we just loop through each vertex, and we're just gonna push back the color we used for that vertex and then return it, and that's it. This part's an easy part because we've already colored them. Now we're just gonna say, okay, which one do we color which? And yeah, the map, if you remember, the map indices correspond to the ring color. So index 0, right, was the 0th one. Yeah, so yeah, map indices are the ranked colors. So like 0 was the 0th one, so that was red, right? And C index is the corresponding color. So like 0 map or 0 becomes red. There you go. So I is our 0th, like if I is 0, right, is our 0th node. So we're gonna get what color we colored it, what color we colored 0, like which color, so or which number. C index is gonna give us the number, right? It's just gonna give us 0 because it's like the 0th number in our list. And then map 0 is red because, like, if we think about that might be confusing. Like we have red as 0 priority, or like the highest priority, so like 0. And C index is going to give us that. It's going to give us 0 because maybe we colored the 0th node red, so it's going to give us 0. And then map is going to map 0 to red, and so it's going to give us the string red, and then we're going to be able to push back red into our vector. So that's what this is doing. Okay. And then we grab the string for each of them and return vector. Yeah, that's how we'd write the code. And so that's how we go through the coding steps. And that's it. And that's all. Yeah. So that is the greedy approach. And this is the entire C++ implementation. So it's basically pseudocode, just runs. But yeah, it might not scale to large, dense graphs because you have to go through all of the neighbors for every node. And if it's very large and very dense, then there are a lot of connections in the graph and a lot of nodes in the graph. That's bad for this because we have to go through all of the neighbors. So that takes a long time. So maybe it doesn't scale well. But this is a much better, still much better though, than every combination, because every combination scales even worse. But how about this poll question? What's the maximum number of colors you need to make a valid graph coloring on a complete graph? What do you think about it? Okay, so the answer for this is B. And maybe this makes sense to you if you just think about like, okay, a complete graph. Oh, that's what I meant earlier. When I said K, the K graph, that's complete. So, silly me. Okay. Yeah, so the graph is complete, right? A complete graph, every node is connected to every other node in the graph. So of course you have to choose every color because like if every node is connected to every other node, well, the problem with that is since you can't color it the same color as anything it's connected to, you have to choose a different color for every node. Because like this node, for example, if we choose red for him, then well, we can't choose red for anything else because it's connected to everything else. And then we have to choose blue for this one. So we choose blue. Well, we can't choose blue for any other node. So we have to go through, and that's gonna be true for everything. And so that's why the most we have to use is V. But okay, an illustration for this is, yeah, a complete graph. A graph where every vertex connects to every other vertex. you need to use a unique color for the graph coloring problem. So you can't use fewer than the number of vertices. It's just not possible for a complete graph. So in some cases, that's the upper bound. So what about the lower? What would be like a lower bound for? What's the minimum number of colors you need to make a valid graph coloring on a connected graph with a large V? So maybe think about this, and the answer for this is actually 2. So maybe it's just a linked list, right? A linked list is a valid graph. So, okay. I mean, if it's something like this, of course, right? Like I can choose red, then I choose blue, and I choose red, and then I choose blue. And you go down the line and you only need 2. Okay. And this is what it might look like. So maybe you can try and think of another example with a large N that only uses 2 colors. But these are some examples of ones to do. Yeah, so even though there's large value for N, like large number of vertices, still only 2 colors are necessary in some cases, like these. Okay, now we're gonna analyze this. So yes, the greedy approach has OV squared time complexity. And the reason why is we go for every vertex, we have to check, we loop through all vertices. And for every vertex, we check if the neighbors have a certain color, which takes OV time because we have to check all its neighbors. And we have to iterate over all possible colors. And remember, with a complete graph, for example, the number of colors is the number of vertices. So that's why this is also OV. And you might have to clear out the vector corresponding to the neighbor's colors. There's also OV time. So the algorithm runs in O of V squared time. And the space complexity is OV since we use 3 different arrays. If we go back to the code, yeah, even this one, we use 3 different arrays. We use like map, index, and taken. And so that's why this is OV space. But let's talk about how this actually performs. So like we mentioned earlier, this doesn't give us the optimal solution, but you might be like, well, why is that? Or how do we know? Well, we can see an example right here. And our algorithm creates a valid graph coloring, but it doesn't necessarily, yeah, it's supposed to solve an optimization problem, like how do we make the best one? Or like use the fewest colors. And that's the idea, is we're trying to use the fewest colors. That's the optimization problem is that we're working on here. Yeah, so our algorithm, does our algorithm always produce graph colorings have a minimum number of colors? The answer is absolutely not. No, it does not. And just looking at the example on the right, we can see that the greedy approach did not work at all in this particular case because we used 4 colors and we only should have used 2. And we could actually scale this example up. So if we wanted to, we could have like 9 and 10 and 11 and 12 that work exactly the same way, and we just scale it up. And maybe the answer is still only going to be we only need 2 colors, but ours could return like many colors. So there are cases where, like, or actually it would return V over 2 colors. So that's of course like not what we want. But again, for most cases, this greedy approach is quite good. And so we should only use the greedy if we're okay with the optimal solution, because it's not always going to give the optimal one. And a common issue with them is it trades optimality for transfer points. There are definitely cases where greedy is absolutely right, like the Huffman tree one. But in the greedy coloring, it's not, because greedy coloring is just not a solution, not something that can be solved quickly. And I'm just going to, this is not as important, but just an aside for those of you interested, I'm just going to talk about, let me make sure there's nothing else first. And then I'm going to, okay, there's not, but I'm going to go ahead and do an aside here for a minute. It's maybe not important, but just like kind of interesting. So in general, the graph coloring problem, you can make, it is an optimization problem, but there's also the decision problem version of it. The decision version of it is given some k, can you color the graph with only k colors? And for k is 2, you can actually, it's not an NP-hard problem. You can just quickly solve it, and maybe you can think of why, because you just need to find a 3 cycle in the graph. But for anything larger than k equals 2, like if I wanted to say, okay, can I color a graph in larger than 2? Or like, can I color the graph in like k? vertices. It's a hard problem, and like it's actually the same as the independent set problem, which is also NP hard. That's why I said that earlier there's like another way to formulate this problem, because there is. The independent set problem is, well, you have an independent set is like set of vertices such that none of them neighbor each other. That's exactly what we're doing here, right? We're just using colors instead. But that's kind of the idea, and like any NPR problem is going to take exponential time to solve, and as a result, if we wanted the optimal solution, it's going to take exponential time, which is generally a bad thing, right? Like, and that's why greedy approach, even though you're like, oh man, it doesn't have the optimal solution, that's okay, because a lot of cases, if you don't want to use exponential time, you have to make some trade-off. And so that's what the greedy approach does here. And so you're going to ask yourself, okay, so how bad can this possibly be? And this is not a tight upper bound, I don't think, but just a simple upper bound on the number of vertices or number of colors that we might use on a graph. Yeah, number of colors, an upper bound on the number of colors we'd have to use is, if we're using the greedy approach, is just the maximum. It's related in a way. You can think of it pretty maybe kind of clearly. It's related to the maximum degree of any vertex, because for any vertex, oh well, +1, because it needs a color itself, but then its neighbors also all need a color. So that would be, well, I guess not the greedy, but that's just an upper bound, or I guess a lower bound actually, yeah, or yeah, on the total number of colors, because always, sorry, so not for the greedy, but this is just in general, right? The lower bound on number of colors is going to be, or no, it is for the greedy. It's because remember, each of those can be colored different way. So the greedy, the upper bound on the number of colors you're going to use is the actual, the largest degree of any vertex +1, because it needs a color itself. But of course, you're going to color all of its neighbors different colors as well. So the number of colors that you use with the greedy, right? Greedy, because if you think about it, the way we actually approach the greedy, it's the maximum, degree of any vertex +1. So that's not important. None of what I just said was important after, so this is an aside. I just thought that was kind of interesting to mention. So maybe good to kind of know, just in general, if you're interested in that. So yeah, that kind of covers that graph coloring. And so yeah, hopefully you got something out of it. But again, everything I said before that was what's important. So if you have any questions about that, of course you can message me about it, right? So yeah, that's about it. These are some extra resources, and hopefully you're able to follow a lot of that at the end. But if not, it's okay. That doesn't matter. The last part, that is, but everything else, hopefully you did. And if you have questions, of course, message me. That's it. Have a nice day.